Swayam Prabha. Digital India. Educated India.
Welcome all of you for this course on fluid mechanics. As in the last class we discussed about conservations of mass and the momentum and its applications. To continue to that conservations of mass and momentum and its applications, today I will deliver lecture on this topic, and also I will solve some example problems to illustrate it how we can use conservations of mass and momentum equations to solve real life problems. Again I can talk about this, that some of the examples are the level of the fluid mechanics what I have been teaching it's a level of the fluid mechanics fundamental and applications in Simbala or close to the fluid mechanics by F.M. White. Let us come back to what we discussed in the previous class, that we discussed that how we can approximate linear momentum equations from Reynolds transport theorems to a specific cases like one inlet, one outlet. So, which is very simplified problems when you have a one inlet and one outlet. And second thing is that, as you know it, the momentum equation is vector equations, but many of the case we can solve the problems in a specified directions or equating momentum equation in a specified directions, not then we can solve the problems. So, we can align the specific axis rotation such a way that using only one equation we can solve the problems. So, these are the simplifications, that the problems where we have one inlet and one outlet, and the momentum equations we can apply for a specific directions. Most important part is that we consider always a steady flow conditions. This is the approximations what we do it, the steady flow conditions where there is no change of the pressure or the velocity distributions with respect to the time. So, it is a steady conditions. We apply the steady linear momentum equations. Again you simplified for the one inlet one outlet case, where the mass inflow will be equal to mass outflow. So, this is very simplified case we will get it. Similar way, when I apply the momentum equation in specific directions, that means as you know it, the momentum equations we can write in three scalar components in x, y, z for Cartesian coordinate system. So, that way we can apply the momentum equations for the polar coordinate systems also. So, if you look at that way, we can apply the momentum equations in a specific direction such a way that we can solve the problems. Flow with no external forces, like a spacecraft, there is no external forces are there. In that case, what simplifications we do it? Then we talk about, when you apply this linear momentum equations, we should follow hints and the tips, like we follow the free body diagrams in solid mechanics. Whenever you apply the linear momentum equations, you have to draw control volume, the control surfaces. How to define this control volume and control surface, whether it is a fixed control volume or movable control volume, how should be the control surface should be there. That should be a major emphasis when you draw a control volumes and the control surfaces, and that hints we should consider it, how these pressure distributions and velocity distributions we should assume it, or we can have a a proper assumptions which is valid for that problems, that we should highlight it. In the last class, we solved many problems like force acting on the sluice gate, force acting on jet, water striking the fixed plate at the centers. Also we talk about the momentum corrections factors, that means beta. How do you compute the beta value, which is the momentum correction factors. Now let us come to today's lectures. What I will talk about that, we will discuss many things with starting with a flow structures in hydraulic jump. Then again I will talk about or repeat the linear momentum hints and the tips. That's what again I will repeat it. Again we will going to solve some of the previous gate questions or example problems based on linear momentum and mass conservation equations. Flow with no external forces, I will repeat that part. Then we will solve one examples cases where no external forces is there, specifically the spacecraft problems. That what we will solve it, and end of the day we will have a summary for these lectures, which is more theoretical. Now if you look, it is very interesting photographs. What is there? It's available. You just type the flow visualizations. It's a great things are nowadays available. If you just type the flow visualizations in any Google search engine, you can see this type of flow visualizations tools are available. If you look at what I am going to show from these photographs, it's clearly indicating that if I have flow jet and there is a mixing of air, there is mixing of air and the water, okay, how the things are changing it. If you look at that, the bubbles what is representing it here, those are all are the air bubbles. So, and if this is the water jet, there is a formations of water air bubbles mixings with water. So interesting pictures are coming up, and if you just visualize the flow, how it is very mixing of air and waters, and that what change the flow systems. So with this just a flow visualizations tool, let's come back to our applications of linear momentum equations. Again I am repeating this part of the tips of linear momentum applications. What are the tips are necessary to do that? One thing you should remember it, this momentum relationship what we get it is a vector equations. That means it has three scalar component, x component, y component and z component. We have the velocity vectors in the three component vx, vy, vz. So similarly we have the force factors which have a three components. The momentum relationship what we have also the three components. But many of the time we result into the scalar components, like writing the momentum equations in x directions, y directions or the z directions. We do that. Second things what I am to highlight is that momentum flux terms. The most of the times when you compute the momentum flux terms, we should look at what is the relationship, what is the angle between velocity vectors and the normal vector to the control surface. If the scalar product of these two vectors is positive sign, that means it will have a positive flux is coming into the control volume. If it is a negative sign, it indicates it's a going out from the control volume. So that is the scalar product of the velocity vectors and the normal vectors to the control surface. That what we consider. Always you sketch the velocity vectors and the normal vectors, then try to find out what is the angle between them. Most of the times what you make it, these two surfaces should have a such a way that the theta, the angle between these two vectors should be 0 or the pi, okay, 180 degree. So it will be easy for us to do vector product. So that way we get either a positive or the negative sign convections. And most of the times if you look at the flow are not a uniform velocity distributions, it is non-uniform velocity distribution. Because of that we should have the momentum flow correction factor beta, because of the velocity distribution is not uniform. But many of the time we simplified it and say that the beta is equal to the 1. We consider it that the flow distribution is uniform, and we do the or we solve the problems. But if we try to understand it, sometimes we can use the beta value, the momentum flow correction factors, when it will be much larger than beta equal to 1. We can use that for especially for the pipe flow. When beta is close to 1, it may help us indirectly not to consider the velocity distributions, but when beta is more than the 1, we should consider the beta values to find out, approximate it, how much the momentum flux going through this control surface. Similar way, when you apply this control volume concept, within the control volumes we do not talk about that, as it can be considered as a trace field and that can self cancelling each other. So, mostly we consider the control volume gross characteristics. Within the control volume we do not consider it how the flow variations are there, the pressure variations and velocity variations, or the density variations. We do not consider that inside the control volume. And this is what very good, it is not approximation, it is a quite valid conditions. When you have the fluid exceeds to an atmospheric and the fluid flow is subsonic, then we can assume it the fluid pressures at that locations is atmospheric pressures. These assumptions is quite valid. So, many of the times we use, whenever the flow jets are going to the atmospheres and we anticipated is that the flow is subsonic. That means the flow Mach number is less than 1. In that case, we can have the fluid pressures, we can assume it, or it is quite valid, the atmospheric pressures. And to appropriate inlet outlet surface, generally we take it flow normal to that. Otherwise, we can solve the problems using the scalar product of the velocity and the normal vectors. It is possible to do it, but it will be laborious to do the integrations part, or it takes time to solve the problems. Now, let us come to solve example 1, which is GATE 2005 civil engineering problems. The problem is that there is a tank or deflectors are placed in a frictionless trolley. Okay, there is no frictions components. Okay. The water issues the water jet, which is have the density of the water is 1000 kg per meter cube. It strike to a deflectors, turns 45 degree. If velocity of jet leveling the deflector is 4 meter per second and discharge is equal to 0.1 meter cube per second, what could be the force recorded by the spring? That is the problem. So, if you look at that, that is what we have sketched it here. There is a tank which is having the waters and getting jet of the waters from this tank, and there is a frictionless trolley. That means there is no frictional force acting on this. The problem is quite simplified for us, and there is a deflector which is making a 45 degrees to turn these things. We need to compute it, how much force which is going to act on this spring. That is the problems. It is very easy problems, we can solve it, but let us follow very systematic approach what I discussed in the last class. We will go step by step. First step is that to classify the problems. These problems is one dimensional flow and steady flow, because the discharge what is coming out from this jet can consider is a steady, flow will be the turbulent, and consider a fixed control volume. Okay. That is for the control volumes I have considered it. So, the force what is acting here, that is a component here. Other the locations, if you look at this water jet is going out from these other locations, we can take it the pressure equal to the atmospheric pressures, and here the shear stress is equal to 0 because frictionless trolley. So, there is no friction force is acting on this. So, it will becomes 0. So, there is no force component is here due to the frictions. So, water jet, that component will commit. That is what the water jet is coming out from this. So, we have chosen the control volume, fixed control volume. Our objective is to compute what is the force recorded by the spring. So, the pressure distributions at the outlet will be the atmospheric pressures. Here also we have a consider the velocity distributions, again average velocity. No doubt there will be a velocity distributions will come it here. After deflectors also velocity distribution will come it, but we here assume it is a uniform velocity and the beta will be the one value for this. Now, let us apply the directly the momentum conservation equations here. If I apply this momentum conservation equation, the sum of the forces should equal to the rate of the change of momentum flux stored within the control volume is equal to the net outflux of momentum flux passing through this control surface, that the Reynolds transport theorems in integral form and in the summations form, as we have inlet and outlets at this. In this case, we can simplify it since a steady problems, this becomes 0, beta is equal to 1, and further simplifications what we have that the force acting in this x directions what we are talking about, that what will be the mass rate of the jet v into cos theta. You can look at the cos theta component will come it as the x directions, and force recorded by spring, if I compute what will be the mass, rho into q. Q of jet is known to us, v is known to us, theta is known to us. We can compute what will be the force acting in terms of Newton. Now, let us go to the second example 2, where we have the water flows through a double exit elbow. Okay, this is elbow type of concept, where we have a v1 velocity and v2 velocity. One is 5 meter per second, another is 10 meter per seconds. Inside the volume of the elbow is 1 meter cube. Okay, the volume of this. What are the vertical and horizontal force component of from air and water on this elbow? If pressure in the free jet is atmospheric and the unit of weight of the water will be 1000 kg per meter cube. Now, if you look at the sketch of the problems, there are the free jet in the two part and there is a velocity here, the velocity here, but the velocity is unknown here. We do not know the velocity of this part. There is a diameters of this elbow part. So, first we have to apply the mass conservation equations, then we will apply linear momentum equations to compute what is the vertical horizontal force components. It is very simple things that here we will apply mass conservation equations, then we will apply two momentum equations, one for the vertical directions, another is the horizontal directions to get what is the vertical force component, what is the horizontal force component. First, let us define the problem. Problem is two dimensional natures, as you seen it that here the flows are coming, there is not change of the flow volume within these. So, we can consider is a steady problems, turbulent, incompressibles, that what we can consider as a flow classifications. We can consider is a fixed control volumes like this is what will be the control volumes. We have the surface like this, we have a surface like this. So, if we have these fixed control volumes, first we will find out the pressures. The pressures at the inlet is given is 25,000 Pascal, at the outlet is pressure is atmospheric pressures, that what is that. So, you have the free jet at these two locations where pressure is the atmospheric pressures. At these 2 points you have a pressure is equal to atmospheric pressure, but at this point I have the pressures which is 25,000 Pascal. newtons per millimeter square. So, if you have that, again we use a concept of average velocities. We neglect the velocity distributions. We use the beta equal to the 1 as for the inlet and the outlet. Then we will apply mass conservation equations. That let us apply mass conservation equations to compute it what could be the velocity at the section 3. So, we are applying the mass conservation equations for these control volumes that to compute what could be the velocity at this point. So, if I apply this mass conservation equations, which are very simple form is rate of mass influx into the control volume is equal to rate of the mass outflux from this control volume. Here we have a 2 free jets, that is what the outflow, 1 inflow what we have. We know the velocity, we know the area, we know the velocity and area, only we do not know the velocity at the section 3. So, we just apply this component of inflow and the outflow, and this is what you will get it. So, density is a constant. So, we will get it A1 V1 is equal to A2 V2 A3 V3. V3 is unknown for us. Simple substituting the area and the velocity of V1 V2, and you can compute it. The velocity of jet passing through this section 3 will be 23.15 meter per second. So, if I apply this momentum conservation equations for this control volume, when I apply this momentum conservation equations, the first things what I writing the control volume equations, Reynolds transport theorems, and then I am simplifying it. So, again it is a steady problems, okay, and I look at the momentum flux in and out, assuming the beta is equal to the 1, and our objective is now to compute the force components. We have the consider the control volume. Inside this control volume, you can think that there will be a frictional resistance from the surface of the wall, but that part we are neglecting it as compared to the force component what is acting it. So, this way we can neglect the frictional force which is there near the wall, that part we are neglecting it to compute it what will be the force component. Now, I apply this force component in the x directions, also the apply in the y directions, and each component you can know it, it has a velocity component will be the 0. In a Vx1 there is only the velocity in the vertical directions. So, if I apply this part, then Fx will come it to the 9539 newtons. Similar way the force components acting on these y directions, that one will be the 7720 newtons. The approximations and all the velocity component, 0 component if you look it, and we have resolved the force momentum flux component as a cos theta and sin theta. We have also considered the force due to the pressures at this point, which is, and also we consider the weight of the fluid here. If you look at this, the weight of the fluid is considered in the y directions, that components are there. The force due to the pressures one also we have considered it, and these are all momentum flux component, that what total what is come in this ones. So, there is a force fx direction and fy direction. We noted that the force due to the pressures at this point we have computed, which is can consider as a gauge pressures, it is not the absolute pressures, and also we have considered the weight component of rho g into the volume. Combining all the terms, we got it, the force acting the y directions will be 7720 Newton. Let us take another examples. A fighter plane being refueled in a flight at the rate of 568 liter per minute of fuel, having specific gravity of 0.68, what additional thrust does the plane need to develop or maintain constant velocity it had just before hookup? The inside diameter of the flexible pipe is 0.127 meters. The fluid pressures in the pipe at the entrance to the plane is 27 kilopascals, and if you neglect the mechanical forces on the plane directly to the flexible pipe and you consider the unit weight of waters will be 1000 kg per meter cube. The problems with what graphically it is shown it in these figures. This is the main aircraft and this is the fueling aircraft, okay, which is fueling the aircraft from these sides. That is what new technologies what is developed it. In air itself we can refuel the aircraft from this part. So, if that is the conditions, what could be the additional thrust does the plane need to develop to maintain the constant velocity between these two? They should move with the same velocity. They should move it with the same velocity, so that the refueling can be done. That is the problems. Now, we try to locate what is the additional thrust is necessary. The problem is now simplified in this part, that there is aircraft like this and it is a hooking it, the fuel hooking to these ones. And if I define the fuel tank and this coordinate of x, y, z, the problems can be considered is one dimensional. Flow is unsteady flow, but we can simplify it to make it the steady flow. Turbulent, incompressibles. So, these three conditions will be there. One dimensional, we are not considering the velocity distributions and all, the unsteady, turbulent and incompressible flow, that is what the classifications. Here it is movable control volume, but since we have the two flights are moving it, with respect to the refueling aircraft, we can consider is a fixed control volume, relative motions to the flight. Okay. So, that the basic assumptions of these type of problems is a fixed control volume which is relative to the motion of the flights. If that is the conditions, the pressure distributions entire outside the control surface we can consider is atmospheric pressures what will be there, like these the problems now. Everywhere you have atmospheric pressures and the pressure, the fuel what is injecting it, it is a P1 pressures having area A1. The everywhere the control surface can be considered is P equal to the atmospheric pressures. The velocity distributions again we can take is average velocity distributions V average value beta equal to the 1. Now, let us apply the mass conservation equations, where is inflow minus outflow, and this case will be V in equal to V out. That means, whatever the inflow of things will come it, that will be the tank what is getting the discharge, A1 P1 will be the discharge to the tank. So, if that is the conditions, we know the discharge liter per second minute, sorry, the liter per minute, this is what the discharge is given to us, the volumetric discharge is given to us, divide by the area, we will get it the velocity, that the velocity part what we have. Now, we have to find out what is the force acting in Rx and the Ry directions. We have the pressure component of here. Applying this Reynolds transport theorems and the simplifying the terms. Here this is the main concept what we have considered it, that there is a change of the momentum flux within the control volume, but the rate of the change of the momentum flux within a control volume is not that significant order as compared with the momentum thrust what is coming from the fuel. So, this component will be there, but it is not that significant. Since it is not significant, we make it to 0 and make it the problems in a steady natures. Then we have a two momentum flux components, one is influx, another is outflux, beta is equal to the 1. So, if I apply it, I will have a simply the momentum flux in the x directions, the pressure into the area, and that what I will get it, and in terms of value I will get it 355 approximately newtons. That what the force will be acting on the x direction. Now, take it another examples which are again simple examples what we are talking about, but is the control volume which is the moving conditions. That means, moving control volume problems we will going to solve it. Like let me have a water jet, if you look at this is a water jet is impinging this normal to a flat plate and moves the right to the velocity v c. Okay, that means these platforms is moving with a velocity v c. Find the force required to keep the plate moving at the constant velocity if jet density is this, the water density is this, jet area is given, and V j the velocity of water jet, and V c the velocity of the frame is respectively 20 and 15 meter per second. Then neglect the weight of the jet and the plate, assume the steady flow with respect to moving plate, jet is splitting into two equal upward downwards half jet. So, these are the assumptions quite valid for a jet flow problems is quite valid. So, as the flow is impinging and making into two directions, vertical directions, one is jet is coming down, another is up, you will have a two dimensional flow, problems becomes a steady, the turbulent and incompressible flow. Movable control volume concept, only the things what we have here to know it, that we will apply these movable control volumes to know it the pressure distributions part. The pressure distributions in atmospheric pressure distributions will be the atmospheric pressure distribution, we will consider the average velocity conditions and the beta equal to the 1. Okay, that the great simplifications we used to do it, and if this is the V1 A2 this cross section, Vz is water is coming into that and it is splitting into two part is a equally part. So, this is velocity of jet, this is what the moving control volume is moving with 15 meter per second, jet is splitting into equally upward half jet, the half of water goes to upward direction, half water goes to the downward directions. If it is that, let us first apply the mass conservation equations. The mass influx is equal to mass outflux. If that is the conditions, you have these values. Okay. Please remember it, we consider here the relative velocity component along the, and it has the V1, V2 velocity which is going out, where is the velocity components, we do not have any velocity components in the y directions, body is only moving in the x directions, that is the reasons we have a relative velocity component what we have used for this does not have any component of relative velocity. So, Aj the area of jet relative velocity is equal to A2 V2 A1 V1 A1 V1, and if is that you can compute it the V1 V2 which will be the equal, and that what will be the 5 meter per second. So, simple calculations can be done to get it that. Now, I am applying momentum conservation equations. We remember it, I need to apply the relative velocity component here as the considerations here, and beta equal to the 1, and I apply the relative velocity component. That what you can look at how the relative velocity components are used for the mass flux and the momentum flux component, and that what is substitute to get it what is the force component. So, the problem is similar natures, only what we are doing it, we compute the relative velocity, the Vxz which is Vj minus Vc, Vg is the velocity of jet minus Vc is the velocity of the platform is moving with Vc, that will be x direction. The flow what is going in a direction of 1 and 2, as you know, it does not have any component in the x directions, we can make it 0. So, only the force we have because of the impinging jet what is working with a relative velocity component, that what we have substitute to finally we got it what is the amount of force acting because of these things. Similar way, the y directions also we can substitute it and apply it as it expected it when you have the same amount of water goes in the 1 and 2, the same velocities, they will cancel each others. So, the net force will be act is 0, the force component will be the positive and the negative. The net momentum flux will be the 0, that the force component will come it. Now, let us come to the example 5th, which is again a simple problems, where a horizontal jet of water strikes a vane, this is the vane, okay, is turned the angle to theta degree, cross sectional area and velocity at the inlet of the vane is 60 centimeters 5 meter per second respectively, neglecting the gravity and viscous effect. Okay. Determine this anchoring force required to hold this vane at the rest or the stationary. This is very simple problems. Okay. There is flow jet is coming, we are making angle theta which is coming out from this jet. The area is given, velocity is given, and we need to compute it what amount of force is required to anchor this vane, so that the vane will be at the rest conditions or the stationary will be there. Flow is a two dimensional steady, we do not know whether flow is laminar turbulent or incompressible flow. Fixed control volume, this is what the control volumes, and the jet is there is the atmospheric pressures and the velocity distributions again we can consider is a uniform. That is what not a conditions when you have the free jet in it going through the vane V, but we can assume it the velocity distributions is uniform, and if that is there we are computing the fast mass conservations, which is very easy things here. Being a steady flow, we will have a mass influx is equal to AO. This is a very standard things as we discussed earlier, and that is what we will show it. Since the speed of the jet remains constant, the area of flow A1 is equal to A2 following the continuity equations as the flow is incompressible. Now, we need to apply the momentum conservation equations, apply the Reynolds transport theorems to compute what will be the force. First, again steady flow conditions, which is standard assumptions we have been doing it for simplifying the problems. For the problems here what we have considered it, and beta equal to the 1. The force component what is acting in the x directions, if I compute the momentum flux Vxn and V1, I can have mass flux, velocity, the velocity component x direction and the mass flux, that what will be equated, it will be this value. Similar way, if I am to compute the force acting in this y directions, I will have mass flux coming into momentum flux in the x y directions will be the 0, influx is not there, it is coming imposing on the x direction, that is 0, but the deflected part will have the component, that is what will be rho A1 V square, the sin theta component which will be the 150 sin theta into Newton value. Now, let us come it before ending these lectures, let us have a one examples, very interesting examples of deaccelerating the spacecraft before landing on the earth. This is what very interesting problems. That means when you have a spacecraft, there is no external force acting on that, and if you have that, there is a multiple inlet and outlet. You can write the linear momentum equations, sum of the force in the systems is equal to 0. You will have a these 2 points. The rate of the change of the momentum flux within the control volume is equal to net outflux of momentum flux passing through this control surface. That is what is written here. Rate of change of the momentum within a control volume is equal to the difference between the rates of incoming, outgoing momentum flux rate in absence of external force. This is what the text, this is what mathematical expressions for this. So, if you assume it is a mass of the control volume is m, which remains constant, then we can write this part is mass of control volume dV by dt, that is the accelerations. So, mass of control volume into the acceleration. The thrust of the force will going to act it is force acting on the body, the mass body into the accelerations, that what net outflux of the momentum flux which is going out from this. This is very interesting problems, we will consider it when there is no external force acting on a control volume, even if you have a multiple inlet and outlet. Let us see this, the figures, what is showing it that when a spacecrafts are landing on the surface, it deaccelerated. It deaccelerated the terminal velocities and then it land on the earth or the any planets. So, how do you deaccelerate it? That is what we do it to deaccelerate that is the problems what we have considered it. A spacecraft with a mass of 15,000 kg dropping vertically towards a planet at a constant speed of 600 meter per second. To slow down to spacecraft, a solid fuel rocket at the bottom is fired. Combustions of gases leave the rocket at a speed, constant rate of the speed of 90 kg per second. This is the what the mass rate is going on. The velocity will be 2500 meter per second relative to the spacecraft. Please remember, this is what the main point, relative to spacecraft in the directions of the motions. Then if that is what for the spacecraft for a period of the 10 second, this is again or neglecting the small change of the mass in the aircraft, determine the deaccelerations of the spacecraft during this period, change of the velocity of the spacecraft and what is the thrust exerted on the spacecraft. So, if you look at this is the spacecraft, this is what the Mars InSight missions, so how the diagrams what we use from the NASA, that is what we have illustrated. Yes, looking at this problem text whatever we discuss it, the problems like this. There is a spacecraft having 15,000 kg weight, the speed is 600 meter per second, which is injected a mass 90 kg per second mass flow rate and it has a relative velocity with 2500 meter per second. What is the amount of force acting due to that? What is the deaccelerating because of this firing of the gases from this rocket and what is the change of the velocity? That is what we will solve it. Now, the problems is one dimensional because only one jet is there. We can use as a steady problems, turbulent, incompressible. This is a moving control volume related to motion of the space aircraft. Here we are talking about the relative velocities. We are not talking about the absolute velocity of jet, and if it is that we consider the control volumes and try to find out what will be the force is acting because of this firing of the gases from this space aircraft. Now, if I have another assumption as you said, the mass of the discharged fluid is negligible as relative to the mass of the aircraft. This will be the solid bodies moving with a constant mass. Okay. No external forces, the pressure forces can be negligible, beta is equal to the 1, assuming the nozzle is well designed. Okay. So, because a well designed nozzle have a close to the uniform velocities velocity distributions. So, beta will be the 1 and let us apply the Reynolds transport theorems. Okay. in this case, as we have considered earlier, okay, so there is this force component is 0, only the change of the rate of the momentum flux within the control volume, that what will force thrust, that will be the mass of aircraft, and the accelerations, that what will be net outflux of momentum flux what is going out from this. There is no inflow, so we will have a, because of gas injections, we have a momentum flux what is m dot v gas, that what is that will be the spacecraft mass into the accelerations. This way we can compute it, the accelerations will be minus 15 per second squares. So, this is the what the accelerations of the space aircraft in the negative directions, that what is decreasing downward direction. Second problem, part of the problem is that compute the change of the velocity. It is very easy because we know the accelerations multiplied with the dt time, we will get it how much of change of the velocity we will have, which will be minus 150 meter per second, and what will be the force acting on that, which is very easy to compute, and the momentum flux or mass of aircraft and the accelerations we can compute what is the thrust is acting on this. This is what will come to 225 kilonewton force acting opposite directions of discharge of gases. That is what happens it. And let me acknowledge before ending this course is that my 3 PhD students, they have been working hard, drawing the figures, illustrating the figures, bringing lot of examples, discussing lot before presenting you. So, I do acknowledge their efforts, and not to improve the knowledge of the fluid mechanics in, but teach the fluid mechanics in simpler form. That is what is possible because of them. I do again acknowledge their help. Okay. With this, let us conclude today's lecture. Thank you lot.